Artificial Intelligence Doctor. User question. How can explainable AI, XAI, methods be applied to electrophysiology algorithms to provide clinically meaningful insights into model predictions, ensuring transparency and building trust among physicians and patients? Synthesized XAI techniques for clinical electrophysiology transparency and physician trust. Explainable AI is crucial for electrophysiology because of the high-stakes nature of cardiac interventions. Here's how XAI methods can be meaningfully applied. Core XAI techniques for electrophysiology. 1. Attention mechanisms and saliency maps. Highlight which portions of ECG/electrogram signals most influence the model's decision. Visualize temporal windows critical for arrhythmia classification. Show which electrode locations contributed most to activation mapping predictions. Example: heat maps overlaid on 12 lead ECGs, showing which lead/intervals drove an AF detection. 2. Feature importance and SHAP values. Quantify the contribution of clinical variables, age, ejection fraction, LA size, to ablation outcome predictions. Rank which electrogram characteristics, fractionation, voltage amplitude, cycle length, matter most. Provide patient-specific explanations. For this patient, low voltage areas contributed 40% to recurrence risk. 3. Counterfactual explanations. If the AH interval were 20 milliseconds shorter, the model would predict accessory pathway with 85% confidence. Help physicians understand decision boundaries and edge cases. Guide therapeutic decisions. Ablating this additional region would reduce predicted recurrence from 35% to 12%. 4. Prototype and case-based reasoning. Show similar historical cases that informed the prediction. This activation pattern most resembles 15 previous cases of atypical flutter, 13 of which responded to CTI ablation. Leverages physicians' experience with pattern recognition. Clinical integration strategies. During procedure. Real-time visualization of model confidence and reasoning during mapping. Flag uncertain predictions where human expertise should override. Interactive what-if scenarios. Test alternative ablation strategies. Pre-procedure planning. Explain risk stratification. Which factors increase this patient's procedural risk? Transparent success probability estimates with confidence intervals. Identify which modifiable factors could improve outcomes. Post-procedure and follow-up. Explain recurrence risk predictions in patient-friendly language. Help patients understand why certain monitoring or lifestyle changes matter. Building trust through transparency. For physicians. Validation against physiological principles. Does the model's reasoning align with known EP mechanisms? Uncertainty quantification. Confidence scores that prompt closer scrutiny. Override mechanisms with feedback loops to improve models. Compare AI rationale to established guidelines, ESC, AHA/ACC/HRs. For patients, simplified visualizations of risk factors they can understand. Analogies. The AI detected irregular patterns similar to those seen in patients who later developed AFib. Clear communication about AI's role, decision support, not decision maker. Addressing key challenges. Clinical meaningfulness. Explanations must map to actionable insights, not just technical features. High-frequency components in the electrogram is less useful than this suggests scar tissue. Validation. Test whether explanations actually reflect model reasoning, not post-hoc rationalizations. Clinical trials comparing outcomes when physicians use XAI-guided versus standard approaches. Workflow integration. Explanations must be delivered at the right time and level of detail. Avoid information overload during time-critical procedures. Future directions. Hybrid models. Combine neural networks with rule-based systems encoding EP principles. Collaborative filtering. Learn which explanation types specific physicians find most useful. Adversarial testing. Ensure models rely on physiologically relevant features, not artifacts. The key is that XAI shouldn't just satisfy regulatory requirements. It should genuinely enhance clinical reasoning, catch errors, and improve patient outcomes. The best implementations will feel like having an experienced colleague explaining their thought process, not a black box issuing verdicts.